many atoms are in a single drop of water? Did you know there are over 5 sextillion? That's a lot of atoms. Welcome to our unit on atoms in the periodic table. Atoms actually got their name from the Greek for atomos, which actually means undivided. They thought that if you take a plant, say we chop it up into the smallest bits, we'd get to what's called an atom. Atoms actually make up everything, and we've actually identified 3 parts of an atom. We have the protons, which are positive, neutrons, which are neutral, and electrons that have a negative charge. Now, if we look at the protons and neutrons, they're located in the middle of an atom. We call that place the nucleus. The electrons are on the electron cloud, the area outside of the nucleus, and we'll talk more about that later. Now, these atoms, there are different ones. So if I'm making up a molecule, or say a human, they're made of different atoms. We call these different atoms elements. And if we actually look in nature, we can find 92. Now, I'll stop there because some people argue that there's 93 or 94. Most people agree with the 92 natural elements. The rest of the elements, we found them other places, or we've made them in labs. Now, we take these elements and we put them on the periodic table. This is a great tool to actually organize the elements, and they're organized by their atomic number. The atomic number, if you don't know, is the number of protons in an atom. Take, for example, hydrogen. It has 1 proton. That's its identity. And so therefore it's number 1 on the periodic table. Number 2 would be helium. It has 2 protons, and therefore it's number 2 on the periodic table. And we could go through. There are 118 different elements on the periodic table. Also, neat little fact. The periodic table is actually started by Dmitri Mendeleev. And ironically, we actually do have an element named after him. How do elements get their name? For one, they might be made up of famous scientists like Mendeleev. They might be made up of Einstein or Einsteinium. Now, none of these elements have actually been named after the person who discovered it. Some elements get their name from Old Greek or Latin. For example, gold. They have the symbol AU. If we also look at others, it might be from German folklore, like cobalt and nickel. We might also look at their properties for color, or maybe even the smell. Now, when we talk about their periodic table, we use different terms. Instead of saying columns, we call them families or groups, because they have something in common. The rows we call periods. Now, if we take a look at the first 2 families or groups, we call those the alkali and the alkaline. These are highly reactive metals. So, if you want to see which ones are the most reactive, we actually look in the bottom left of the periodic table. If we look in the middle, we call these transition metals. These elements are great at making compounds and at sharing electrons. We'll talk more about that later. However, think of these as kind of like the metal Legos. They're great at stacking, they're great at building different compounds. On the right-hand side, we have a lot of different types of elements. We have nonmetals, which include the halogens, which are salts, kind of like bromine and chlorine. We have the noble gases, which include argon and helium. These are ones that actually are really stable and are gases. On the bottom of the periodic table, we have actually 2 periods, which are the inner transition metals. These are actually really unique elements. A lot of those have radioactive properties. Now, if we look closely at the periodic table, take for example hydrogen. If you look, it is the atomic number 1. That means it has 1 proton, and if it's a neutrally charged element, it has 1 electron. However, how many neutrons does it have? If we look at the atomic mass, it's an average, saying, hey, all the hydrogens we have, what's the average mass of the nucleus? And if you remember, the protons and neutrons make up the nucleus. So if we know hydrogen, for example, has 1 proton, if the atomic mass is 1.0079, we know that more often than not, if we round, there are 0 neutrons. Now, if it did have a neutron, we call that an isotope. Isotopes are elements with different amounts of neutrons. Take, for example, carbon. Carbon has 6 protons. However, did you know that it could have 6 neutrons, 7 neutrons, or 8 neutrons? That would make the mass for carbon be carbon 12, or carbon 13, or carbon 14, depending on the number of neutrons. We call these isotopes of carbon. There are a lot of elements that have isotopes. Now, isotopes are unstable and tend to be radioactive. We use those in a lot of different places. We can use those to kill bacteria. We can use those in medical radiation. Sometimes even in tracers that actually trace the chemicals throughout a body. We might even use those for smoke detectors, or even in dating, archaeological dating. Carbon is a big example of archaeological dating. So if something died 60,000 years ago, we can use carbon. If we measure how much there is, we can actually see how long ago it died. Because of an isotope, it's unstable, it falls apart, so it will not last forever. Now, when we talk about atoms, we also talk about fusion and fission. The idea of fusion is the fact that we have two atoms, and if we were to combine those into one atom, that would be called fusion, or we are fusing those together. In extreme conditions, this is possible, and we might actually get what's called a fusion bomb, or a thermonuclear weapon. It has a gigantic amount of power and energy because of the mass that's lost when those two are combined. Or take, for example, a nuclear power plant. Currently, we don't have any fusion power plants, but one is actually being built. And one of the benefits to it is a reduction in the amount of fossil fuel usage, and it should be less radioactive. However, there are a lot of dangers. We actually know that from fission. So if we had an atom, and instead of having one, it's split apart, that's called fission. Alright, it has two S's, if that helps you remember. It goes from one into two. Now, we actually do have fission power plants. Usually we use uranium, and if you've been kind of to 3 Mile Island or seen it from a distance, that's a nuclear power plant. Using uranium, they are able to harness the energy from it. Now, one of the problems is, if that were to be released, there's a lot of radiation released. We've actually had 3 major accidents. The first and the largest was actually in Chernobyl, which is in current-day Ukraine. Radiation was released in the air, and there was almost like a meltdown. So that means a lot of people were exposed to high amounts of radiation. Matter of fact, there were dozens killed within the first week because of radiation. Now, over the years, we've come to understand that there's been millions of cases of cancer because of that radiation release. The second was Fukushima, Japan. Again, we had a tsunami come in, but there was a problem with the backup for the power plant, and we actually had radiation released again. That's also creating some vacant towns nearby where the radiation levels are too high. And the third, I'd like to think we're lucky, was 3 Mile Island. There was a small dose of radiation released. Now, there were no instantaneous deaths as maybe the other 2 power plants. However, there have been some reported cases of cancer, or increased chance of cancer because of that radiation. Now, there's no documented, as they'll say. However, there's been a lot of stories around this area in Harrisburg that people have increased risk of cancer because of that. Now, earlier we talked about the electrons being in an electron cloud, or outside of the nucleus. This area has electrons whizzing back and forth. Now, for our purposes, we're going to use the electron cloud diagram. This shows you different levels or rings that show you where the electrons are located. Now, most electrons have more than 2 electrons, and that's the least amount that we can find on the first level electron. So, hydrogen, it has 1 electron on the first level. Helium has 2, however, that's maxing the first level out. So if you go to the second level, it can house a total of 8 electrons. The third level houses up to 18 electrons. The fourth, 32 electrons, and the fifth, 50 electrons. Now, we're going to start at the first level and maximize it before if we have any remaining electrons. So keep in mind, as we get more electrons, we go further and further away from the nucleus until each shell or each level is maximized. Now, I do want to mention this, that there are kind of subdivisions to each level. That gets a little bit more important as we get into talking about, hey, how are electrons shared and how do they leave, or how do they swim around? But we'll get to there when we're talking about element bonding.